Okay, find the derivative of this line, y equals negative x plus 3. Before we actually do this, I want you to actually think about what you think the answer is. Okay, it is a line. So what do you think the derivative should be? Now what I'd like you to do is let's think of this as f of x equals negative x plus 3. I'm going to write the definition one more time here. So f prime of x, or y prime of x, or y prime, sorry, is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. What I'd like you to do now is pause the video, work out what this is, and confirm that what you got is what I did. I'm going to pause the computer too, and I'm going to write down the answer. But go ahead and pause it and work this out. Okay, compare your work to my work, and hopefully you got the same answer. That this derivative function is in fact not a function in terms of x, it's a constant function. Okay, the derivative f prime of x is equal to negative 1. Should it be surprising to us that this derivative is constant? I hope not, because we're thinking about a line. A line has constant slope. Okay, so make sure your notes match mine. And let's move on. So this process of finding the derivative function, so what we've just been doing the last few problems, this is called differentiation. So that's the verb of it. We say that a function is differentiable at x if the derivative exists. So think about the derivative has to exist. That's really just saying that the limit definition exists, right? We know that from last unit, sometimes the limits don't exist. So it's differentiable if the limit exists. A function is called differentiable on some open interval if it's differentiable for every point in that interval. Okay, and then the domain of f prime is the set of points in the domain of f for which the limit exists. And if f prime exists at every point in the domain, so on all the values, all the domain of f, then we just call f differentiable. So this language should sort of sound a lot like what we were talking about when we were talking about continuity, right? We could say a function is continuous at a point. We could say it's continuous on an interval. And if it's continuous everywhere, we just say it's continuous. So this is the same sort of thing with differentiability. And as we've already said here, we read f prime as f prime. Moving on to some other notations, there are some others. The most common ones that you're going to see are f prime and y prime, right? We've already seen those. The others, these three right here, these are due to Leibniz, okay? And they are definitely valuable and will become more and more valuable as you move through calculus. So when you get to like multivariable calculus, for example, you're pretty much only going to stick with Leibniz's notation. So this dy dx, this notation is read as the derivative of y with respect to x. Now, we're only going to ever have one variable in this class, but with this with respect to x thing becomes really important when you've got lots of variables in a function and you need to specify which function you're taking the derivative with respect to. Okay, so the dy dx or the df dx, taking the derivative of the function f with respect to x. These x's in the denominator are all just telling you what you're differentiating with respect to. The default is, when we only have one variable, that it's that one variable. This notation, the derivative with respect to x of f of x, these two things mean the same thing. They're both saying, no, I don't know, whatever. Ignore my computer. I'll have to erase that later. These two things mean the same thing. They're saying take the derivative with respect to x of f of x. This is nice for if you don't want to have an actual equation. So if I just said something like, I want to know the derivative of x squared, and I don't want to actually say, oh, this is f of x equals x squared and then find the derivative. I just want to directly take the derivative of this expression. Now we know from the earlier question that the slope function is 2x. So this notation here is useful for taking the derivative of an expression instead of a fully defined equation. Okay, so a lot of what I wrote here in the notes has to do with what I just finished saying. So this notation due to Leibniz becomes more useful as you have more and more variables. And this notation really emphasizes this idea of rise over run. dy dx is really thinking about the limit as delta x goes to 0 of this change in y over change in x. This is right here. This is our classic slope rise over run function. Okay, so the notation is really emphasizing this connection between the two. Okay, so we can see that these notations all mean the same thing. Now, if you want to look at the notations for what we have at a particular point, right? So if I want to look at the derivative at some x value c, I can just evaluate the slope function at c, Or if you're using Leibniz's notation, we usually use some sort of straight bar or brackets with the function value where we're evaluating it written down as like a subscript.